Okay, so far we've gone over the first law of thermodynamics, which is that energy is conserved. Don't forget delta E, the change in energy is equal to Q plus W, which is work plus heat. We're going to start introducing a couple new terms, okay, some new vocabulary. First one is spontaneous. Any reaction that occurs without any outside intervention. For example, if I drop an egg, it will spontaneously just fall and break. The reverse is non-spontaneous. Okay, the broken egg, is not going to join back together and then jump back into my hand. Okay, so we've got spontaneous reactions, non-spontaneous reactions. Reversible process. Change can be restored to its original state by exactly reversing that change. Okay, for example, ice water at 0 degrees Celsius. What is water doing at 0 degrees Celsius? Well, some water is freezing, some water is melting. Okay, so that would be at an equilibrium. So equilibrium are reversible processes. An irreversible process cannot simply be reversed to its original state. Okay, gas expanding. I cannot just put it all back together. Okay, for example, if I have ice cubes at 25 degrees Celsius, they will spontaneously do what? They will melt. Okay, it's irreversible. At that temperature, I cannot get it to go back to become an ice cube. Processes in which the disorder of the system increases tend to occur spontaneously. Okay, so here's a new word now, disorder. Gas expanding. Okay, when you have a gas expanding, it's going all over the place. It's increasing its volume, so it's becoming more disorderly. When ice melts, it's making a mess. It's going from a solid to a liquid, which has more movement. It's becoming more disorder. When you have a salt dissolving in water, all of a sudden you've got ions floating around. It's becoming more disorderly. That happens spontaneously. Entropy. So this is our new word here. Entropy, which we will call S, is the change in disorder. It's the measurement of disorder. The change in randomness, if you will. The more disorder, the larger the entropy value. And then once again, delta S is S final minus S initial. Your final entropy minus your initial entropy will be your change in entropy. So if your change in entropy is a large value, larger than 0, that means that the final state is in more disorder than the original state. If delta S is less than 0, then the final state is more orderly than the original state. Remember, delta S is the measurement of disorder. So if you look at this situation right here, what's going on? You've got liquid water turning into solid water, and solid water turning into liquid water. This is a reversible process. So its delta S is actually 0 because it's going in both directions. This, however, you've got aqueous ions turning into a solid silver chloride precipitate. So you have two things coming together forming one. So that's becoming more orderly. Therefore, its delta S would be negative. If you have a solid melting, it's becoming more disorderly. So therefore, delta S is positive. A liquid vaporizes. That's becoming more disorderly. So that would be positive. A solid dissolves in water. That's becoming more disorderly, therefore positive. A gas liquefies. That's becoming more orderly, therefore delta S would be negative. For a process at constant temperature, the entropy change is the value of Q reverse divided by the absolute temperature at which that takes place. We're going to do these in class tomorrow, so I'm just going to skip these. We'll do the math part tomorrow in class. Here we go. The second law of thermodynamics. In any reversible process, which we just saw one, delta S for the universe is 0. In any irreversible process, spontaneous process, delta S will be positive for the universe. Okay? Remember, we've got the system and the surroundings. If you add them together, that's the universe, if you will. On a molecular level, okay, there's three types of motion that you need to be familiar with: translational motion, vibrational motion, and rotational motion. Rotational motion is exactly what it sounds like: molecules spinning, rotating. Vibrational motion is the movement of atoms within a molecule, just vibrating back and forth. And translational motion is the actual movement of it going from A to point B. If I increase the temperature, then molecules tend to move more, and therefore entropy increases. The more movement, the more disorder you have. So as this is temperature down here, let's see if you can see this better here. No. If I increase the temperature, things start moving faster. If things start moving faster, it's becoming more disorderly. Okay? This would be melting, going from a solid to a liquid. So notice that I'm going from a solid to a liquid, so I jump up in my entropy. It's becoming more disorderly. This is just a liquid being heated. Then I get here, and now all of a sudden we're boiling. Look at the huge jump in the boiling and the entropy value. Okay? Obviously, when you go from a liquid to a gas, there's a ton more movement. You're becoming more disorderly. And so there's a jump in the entropy value. The third law of thermodynamics: the entropy of a pure crystalline solid at absolute zero is zero. Okay? Absolute zero is a theory. It's never been proven before, but it's been very, very close. That is that at this temperature, 0 Kelvin, everything stops moving. There would be absolutely no movement, no translational, vibrational, or rotational whatsoever, and therefore the entropy would be 0. In general, entropy increases when liquids or solutions are formed from solids. If you go from a solid to a liquid, you're becoming more disorderly. Gases are formed from solids or liquids. If you go from a liquid to a gas, you're becoming more disorderly. The number of molecules of gas increases during a chemical reaction. If you produce gas, if you're increasing your amount of gas, you're becoming more disorderly. So let's look at this one. I have a solid that turns into a gas. So you're becoming more disorderly. You also have one thing making two things, becoming more disorderly. So its delta S value would be positive. This one, notice I have gases turning into gases, so that's nothing, that hasn't changed. But this, I have 4 gas molecules turning into 2 gas molecules. So that's becoming more orderly. Therefore, delta S would be a negative value. Standard molar entropies. Okay, if you look in the back of the book, just like we did with enthalpy or enthalpies of formation, there's also entropies of formation. Absolute entropies for substances in their standard state. Unlike enthalpies of formation, the standard molar entropies of elements are not 0. That's because everything has movement, therefore everything has disorder. The delta S, or the S value for gases, obviously are greater than those for liquids and solids because they have more movement. S generally increases with increasing molar mass. The heavier things are, the more it has, therefore the more movement, therefore the more disorder. And S generally increases with the number of atoms. The more stuff you have in something, the more movement you have, the more disorder you have. So we're going to end up doing the same thing we did for delta H. For delta S, it's going to be the sum of the products minus the sum of the reactants. So when we look in the back of the book, now we're going to be looking at our S values, our disorder values. Okay? So I would like you to calculate the delta S for the synthesis of ammonia. If you'll remember, we said earlier, we have 4 molecules turning into 2 molecules, so it's becoming more orderly. So I'm going to predict that the delta S value will be negative. So I'm going to look up ammonia, multiply it by 2, since I have 2 of them, minus the sum of my reactants, nitrogen plus 3 hydrogens. So I've got 2 ammonias minus 1 nitrogen and 3 hydrogens, and I get an answer of negative 198.3. And please notice that the units for entropy are joules per Kelvin, not kilojoules. Enthalpy is measured in kilojoules, entropy will be measured in joules.